now we'd be able to find the volume of something weird like this, a little yoga block. We would need, obviously, this function, right? We would find this distance, that would be one dimension, and then if we imagine slicing this, we'd get rectangles, so all we'd have to do is measure the height of the rectangle. So the area of each rectangle would be this distance times the height. That would have to be given or measured. And then the thickness, of course, would be dx. And we'd integrate to add all those up. But what if I had the orientation, not with respect to x, but with respect to y? What if I knew these equations with respect to y? Well, that wouldn't be too bad. I'm just slicing now perpendicular to the y-axis. I would do it the same way. I would find the area of each rectangle would be this length, this function minus this function, right minus left, times the height, which we'd have to be given or figure out. We were actually physically measuring something. And then what would the thickness of each rectangle be? What would the thickness of each rectangle be? Oh, it would be dy. So we can find volumes with known cross sections either with respect to y, when your slices are perpendicular to the y-axis, or with respect to x. Let's find the actual volume of this yoga block, shall we? All right. And we'll do it with respect to y. So let's say that this function right here can be defined as 2 times the sine of 1/2 y plus 1. So it's a function in terms of y. Y is my independent variable. Let's say that this curve is that same curve reflected over the y-axis. And I actually measured this, and the height of this volume is 3 inches. So that would mean that each cross section would be a rectangle, right? Each cross section would be a rectangle with a height of 3. So, boom, boom, made some nice rectangles here with my sticky notes. Okay, so I have different widths of rectangles, and the height of each rectangular slice is 3 inches. All right, so we're going to do this the way we've been doing this. We're going to find the area of each one of these rectangles, and then multiply it by the thickness, which in this case is going to be dy, to get the volume of each rectangular slice. And then I'm going to add up that infinite number of slices from my smallest y value to my biggest y value, in this case from 0 to 2 pi. All right, how do I find the area of a rectangle? Well, it's length times width, or base times height. So my height was given, the height of each of these rectangles is 3 inches, and the base is going to be the distance from the right curve to my left curve. All right, so the area is going to be the height, and I'm going to put the height out here since it's a constant, times the base, and the base is my right curve, so I'm just going to call that x1 minus my left curve, which is x2, and I'm integrating with respect to y. Alrighty? And I'm doing this from 0 to 2 pi, from my smallest y value to the biggest y value. All right, so when I simplify this, I end up with this. I think I did that right. Just subtracted, distributed the negative. We can either do this by hand or we can do this in our calculator. And again, when you do something in your calculator with respect to y, the calculator doesn't know. You can just throw x's in your calculator. It will give you the correct answer This is going to give us a volume of approximately 28.566 cubic inches. Very cool.
They just keep holding me.
So really, when you compare the formulas, if you will, they're exactly the same. If your slices are perpendicular to the x-axis, your thickness is going to be with respect to x. If your slices are perpendicular to the y-axis, your independent variable is y, so your thickness is y. You go about it the same way.
Won't let go, holding